Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all of you. As I promised last week during the online session, so this week will be our test weeks. However, I need to deliver some kind of at least very short video or 1 hour video about the continuity of the CTOD testing, so how we deal with that, as well as how we want to calculate the real, in terms of the calculation of the CTOD measurement. So I just want to recap a little bit on the CTOD. So this is the last week's slide. What does it mean by CTOD? CTOD means crack tip opening displacement. In our case, is the measurement testing. So you'll see that from here, the main objective, for this is to determine the critical crack at the onset of the crack extension. So it means that the aim is to get the critical. So this is the aim, so to get the delta critical. So this is done by measuring displacement at the mouth of the crack using a clip gauge, and then we will implement this UiTM E1820 standard that represent the total measurement procedure for the CTOD, both in the compact and SNB specimen. So in our case, we will see whether we want to apply the SNB or in terms of the CT specimen. So the machine notch is pre-cracked, produced under the carefully controlled fatigue loading. So of course, once we fabricate the specimen, there are conditions that need to be fulfilled, which is we need to develop, or we need to create the pre-cracking, so by means of the fatigue pre-cracking under the certain load that is given here. The specimen is then gradually loaded until the maximum load, and we have to plot the load versus the clip gauge displacement, or we can say that this is the load. In our case, this is the load versus CMOD. I think the last time I already discussed about the CMOD. CMOD means the crack mouth opening displacement. Okay, so if I scroll down a little bit for the slide, so this is the ones that you will obtain. So since that we are talking about the load versus mouth opening, or we call it SCM in front, crack mouth opening displacement. Okay, so you will get the other three graph. Either you will get the graph for the pattern A, pattern B, or pattern C. Here we have some kind of description. Last week I already discussed about this one, so I can skip it because this is from the experiment. So you will conduct it. The first thing, you have to fabricate it according to the standard 1820 standard. Either it's for the compact tension or for the SNB specimen. Then we apply the pre-cracking using the fatigue pre-cracking by the certain requirement with certain load, certain frequency and whatsoever, and after that we put into the machine. And for the SNB, for example, we just put it in some kind of the span itself and put a load, and until it fracture, you will get this kind of three different types of pattern. So from these three different type of pattern, we will investigate about what will be the maximum load. In our case, the critical force, the critical load. So from this critical load, we can do the further analysis. So let's see here. So this is what we will deal for the CTOD. So this is the formula that you will use. So whereby we're talking about the delta critical is equivalent to the delta elastic plus delta plastic. So we will split into two parts. So this is the arrangement for the SENB. This is for SENB, which is, what does it mean by SENB? Single edge notch band. So this is notch bending. However, the load is coming from the bottom and put it up to upward, in the upward direction. We have a clip gauge. We measure the mouth opening, not the crack opening, not the crack tip opening. We are measuring the mouth opening rather than the crack tip opening. So you will see that the plastic deformation at the crack mouth VP. So this is the plastic displacement related to the plastic CTOD, and you will see that this is kind of derivation because the delta P means delta P or VP is the same in this case. So we are measuring the plastic deformations related to the either CT or SENB. Okay, so now I proceed to more detail about the equation. So since that we know the delta critical, so this is the delta crit means critical is equivalent to the delta elastic plus delta plastic, and the formula for the delta elastic, this one, so this is meant for if we find out that 1 minus Poisson ratio to the power of 2, that represent the plane strain condition where we assume that the specimen is thicker, so as compared to the smallest one. So the formula is K1 square 1 minus Poisson ratio to the power of 2 and divided by M sigma yield strength multiplied by E. So M is depending on normally M we can assume as 2 because this is a thick specimen, plane strain. So plus RP. RP is not the plastic zone radius. In our case, RP is the rotational factor, and normally we assume is equivalent to the 0.4. And W, you know, W is the width of the specimen. A is the crack length. A is the original crack length. VP is this CTOD, plastic displacement. And Z will be if we get higher level of this one, so normally we always assume Z becoming 0 in our case. Alright, so this is the formula that we use. You have to memorize this formula. Delta elastic is equal to, again, so this is the stress intensity factor, the power of 2, and you have to multiply by 1 minus Poisson ratio to the power of 2 divided by 2 times sigma yield strength times E, and this is the plastic calculation. So the delta for the plastic calculation, you have to fulfill this one. And since that K1, so how to obtain K1? So we have to refer to the equation. For the K1 is equal to PS over BW to the power of 3 over 2 multiplied by the function A over W. This only valid for SE and B specimen. So if we change into CT specimen, you will know that the equation will become different. So for the CT specimen, the K1 will become P divided by B multiplied by W to the power of half only, and you have to multiply by the function of A over W. So this is different. So you have to refer to the chapter number 2 so that you will align with this kind of formulation. Okay, so now let's talk about a little bit on how to solve this problem and the plastic component VP. So this is the VP, or in our case, some books is referring to the delta P, is obtained from the load displacement curve by constructing a line parallel to the elastic load line as illustrated. You will see this is the load versus CM on the crack mouth opening displacement. You will obtain this one, but before that we change this one. So this is the graph that you will obtain, okay, and follow, and you'll get the maximum. So this will become your P critical. What you can do here, so what we need to do, first thing first, to the elastic line you have to draw the straight line. So this is the elastic line. Sorry, my pen is becoming like this, and you have to get the offset from the elastic line. Offset means the same distance, so this is the offset line. See here, and what you need to do, you have to measure this point from the offset line, from here to this one. This line represent the VP value, and VP is the displacement value in unit of M, or in unit of millimeter, or in a centimeter. So what you need to do, so you have to offset the line. So offset, I name it as the offset the line. So please read about the offset in terms of the how you want to develop the offset situation. So VE is something like elastic displacement. So we are not talking about the elastic displacement, we're talking only in the plastic displacement. So this is what you deal. Okay, straightforward. So just jump into the first example. So this is the first example here. We have a 3-point band. So when I mentioned about 3-point band, is related to SE and B specimen. Okay, and in our case, when we talk about SE and B, so you have to know how to solve it. So we have the span distance with the crack, the plate width 6 centimeter. This is the crack length, is the thickness 3 centimeter, is used to determine the C critical crack opening displacement, which is we are talking about the CTOD of a steel plate. So the material is steel plate according to the BS standard of 5762. I think this is the equivalent to the ASTM 1820, so no worries about it. So the load versus crack mouse displacement, which is the load PV, means the P means load, V means displacement record of the test, is shown in the figure below. Right, so already shown here, and bear in mind, so this is the CMOD data, crack mouth opening displacement. So this is the force, right? Determine the crack opening displacement, which is delta C, when E is equivalent to 210. So the given all this information, E is a Young modulus of 210 gigapascal, Poisson ratio of 0.3, as well as the yield strength is equivalent to the 800 megapascal. So this is the data, and we are quite sure that we have the formula already. So delta critical is equivalent to the delta elastic plus delta of plastic. And each component, we know it already since that is given to you this Poisson ratio. So what you need to do for the elastic, you know that the so K1 to the power of 2, what else, divided by 2 sigma Y, you multiply by E, if I'm not mistaken, just check it back, and you have to multiply by, what else here, you have to multiply by 1 minus Poisson ratio to the power of 2. So be careful with this one, and you have to plus with delta plastics, mean a little bit complicated. I have to fill this one. Okay, RP. So RP W minus A. So you know that RP rotational factor. Okay, so W minus A. Okay, W minus A. What else? So multiply by the plastic deformation, VP, divided by, we follow the same pattern, RP W minus A, okay, W minus A, and then plus A again. So plus A again. Okay, so now the challenge is, first thing first, we have to solve for the we have to identify the P maximum. So in our case, this is our P max, P critical, PC, or is equivalent to the P max in our case. This is our P maximum. So it's equivalent to, I think, so if I that this is a 35, I can say that 31 or around 32, around 32. That will be the P max. Okay, let's move to the next slide, how we solve it. So this is the formula, so just keep it from the slide number 14. So this is delta elastic K1 square. So now the challenge is we need to calculate the K1 first by knowing that the specimen has been given here as a SENB. Alright, so this is the formula for the SENB. PS, so P is the maximum force, maximum load, you multiply by the span distance, divided by the B, the thickness of the SENB specimen, and W is the width to the power of 3 over 2, and you have to multiply by the function of A over W. So we know that the P is estimated by 31.6. Bear in mind, I am estimating the value is around 32 kilonewton. In this one, we assume as a 31.6 kilonewton, which is quite accurate. So I don't have this capability to idealize this kind of accuracy. So I just use a 31.6, or you can straight away using the 32 kilonewton. Doesn't matter in our case. And for A over W, if you calculate A over W, we know that the A is equivalent to 3 centimeter and W is 6. So it means that if you calculate the A over W, it means that the unit is the same. A means 3 and divided by 6. So obviously the answer is 0.5. And there is no unit because this is a ratio between 2 units of length. So A over W is a 0.5 in our case. So we can estimate using the formula because here we already calculated here. So this is the very long formula, just plug in. Bear in mind, in test for example, we will give you this kind of very long formula. You have to input all this A over W and have to calculate it. So hence by means of the long calculation here, you will obtain this kind of geometrical factor, in our case FA over W as a 2.66. and then what else? So K1 can be calculated as, and simply we put P. So in our case P is a, this is P, so this is the P value 31.6 kilonewton. You have to multiply by S as the span distance. Back to the original data, S mean in our case is 25 centimeter. So we'll convert to meter, is a 0.25 divided by B, multiply by the W to the power of 3 over 2, and then you multiply by this geometrical factor here. And what you will obtain? You will obtain this value. So this is the, this is the K value. So this is the K value. So I need to, okay, so this is the K value, which is 47.7 megapascal square root meter. Alright, so K has been solved, so no worries. K kita dah ada, we have it already, the K, and we have to multiply it, the power of 2. Poisson ratio we know it already, yield strength also we know, as well as the model density, and straight away we can calculate for the elastic deformation. So you see here, deformation is 0.006 in the unit of meter. Alright, so it means that is approximately to 6 millimeter. Around that is quite small for the elastic deformation. Okay, 47.71 minus 0.3. This is millimeter, in millimeter, so because 800 everything is remain, so this is in the unit of 0.006 millimeter, is quite small, so that I can say that the elastic displacement, the influence of the elastic is quite small, almost that can be neglected in our case. I mean, the challenge is to calculate the plastic component. So have a look on the plastic component here. The plastic component of the crack mouth displacement, which is VP. Bear in mind, the formula for the VP is this one. I already put it here. RP, you multiply by the W minus A, you multiply by the VP. The challenge is now to obtain the VP value. The rest it should be taken from this one, because we know the RP can be used as a we can use as a 0.4. Okay, no worries. This one, W we know it already, 6 centimeter. You convert it to meter or millimeter. A we know it as a 3 centimeter. What else is the only unknowns that we not quite sure in our case now is a VP. Then we have to investigate about the VP. So we need to talk about VP, and we know the PU. So what we can do, first thing first, you know it. So what we can do here, we draw the straight line from the 0, 0. So you can use your ruler, you can use the protractor, whatsoever. Make it any available tools for you, just to get the straight line like this. And this is the offset. Offset means the same distance from the bottom up to. So this is the offset distance. Offset. This is the offset distance. So if we measure by means of ruler or whatever, so it can be around 1 mm. So this is already mentioned here, is around 1 millimeter. So now we know the VP already. Straight away we can substitute into the formulation. This is the RP. This is your RP taken as the 0.4. This is W, which is 6 centimeter. This is A, which is 3 centimeter. Then you have to multiply by the VP is a 1 millimeter. So you can convert into millimeter, or you can convert to the meter. In our case, this is 1 millimeter. You have to convert into meter. Then 1 times to 10 to the power of minus 3 divided by 0.4. So 0.4, this one 0.06 minus is already been taken K here. So it's been solved directly. 0.4 multiplied by in the bracket itself, and you have to plus again with the A here, and you will know that you will obtain 0.286 millimeter. Then you can compare between these two value. Okay, from elastic value, which is the effect of the displacement of the elastic value, is very less, which is 0.006 millimeter, when compared to the delta P is quite big, which is 0.286 millimeter. So it shows that in the case of EPFM, then almost all the material has been transformed into the plastic zone. So that's why you will obtain the 0.286, which is very high, very in terms of value, is very large as compared to the delta elastic. Then we combine everything, then you know that the delta elastic plus delta plastic, you will get the 0.292 millimeter. So this is how we'll solve the CTOD in our case. So we want to have the delta critical. I hope that you understand the concept of CTOD from the experiment. How can we convert from the data from the experiment, from the load versus crack the crack mouth opening displacement, we convert into the full calculation of the experimental works. Okay, so it seems to be that we complete the task here in terms of the CTOD. I just want to share one thing. I think this is one of the another question here. Hopefully you can see from this one. So have a look on, wait, sorry, okay, I think they are not sharing this. Okay. I'll just change it here so that everybody will. Sorry. So back to 1. Okay, now we're back to square. Right. So you'll see this is one example from one of the tests. I didn't remember which semester. I think this is more or less the same concept here. Okay. SANB specimen with a W 60 mm, B 30 mm, S 240. So it's obviously this is the case of how should I? Okay. Okay. So I'm not sure because I can't use this one. I try my best to use my screen. Obviously I can't use it because they just keep on okay, let me sketch here only because I cannot use my pen. So you know it. So this is the formula. It is more or less the same. What else is given to you? The sigma y poison ratio RP also is given. Maximum force is recorded is 40 kilonewton, as well as VP also is given here. I think it's quite straightforward here. Okay, so use the formula. It means that the question is determine the crack opening. So obviously it's really easy. So because the formula of Allah, it's quite easy. So we know that, we notice that the formula, so delta C, this is the formula. So delta C is equal to delta elastic plus delta plastic. Sorry, so because I'm using this kind of don't know. Okay, so delta, this is K1 to the power of 2, okay, divided by 2 times sigma yield strength, you multiply by E, okay, and then you multiply by 1 minus Poisson ratio to the power of 2, right? Okay, and then plus, we know that this RP W minus A, you multiply by the VP and then divided by RP, the same, W minus A, then you have to plus A here. Okay, there's nothing strange with that. So calculation for the K1, we know that because this is SANB, so we have a P times S divided by B times W to the power of 3 over 2. Now you have to multiply by the function of FA over W. Okay, so you have to solve for the A over W first. So A over W, we know that the crack depth is 27. So it's a 27 here. 27 divided by W. So 60. You did the same, 27 is millimeter, that will be 60. Okay, so if you calculate here, I just want to calculate it together with you. It's a 27 divided by 60. Okay, point, you will obtain 0.45. So 0.45. So this is A over W, and for the function itself, you have to substitute exactly. Okay, so everything you have to substitute. Let's say, for example, 3, then you have to substitute by 0.45. Sorry, because I'm using my cursor to draw, that's why it's quite slow. To the power of half, like this. Okay, and then you know that. Okay, we know that it's a 1.99. Sorry, because using the cursor is very difficult right now. Minus A over W is 0.45, sorry, 0.45, and then you have to minus 1 minus 0.45. Okay, we know it already here, and you continue as a 2.15. Okay, you continue until the end. Okay, bracket, and close this bracket, and you have to divide it by all these things, to 2, 1 plus 2 multiplied by 0.45. Okay, and this one in the bracket you have to fill it, and then you will obtain, if I'm not mistaken, just check, since that this one I have is, I think the answer is here, you know it already, is a 2.285. So 2.285, 2.285. So later on you have to try it by yourself about this one. So this will be FA over W. Then you calculate the K1 here. We know the P has been given here. It's quite critical. It's a 40 kilonewton. So this is a 40 kilonewton. I just put the unit here. Okay, so P you multiply by the S. In our case, S is a 240 mm. Since that the unit is in a square root of meter, so I convert into meter. So I will obtain 0.24. Okay, and then the formula is, so divided by the B itself is a 30, so it's a 0.03. Okay, and W is 0.06. Okay, and to the power of 3 over 2. It's not multiplied, so this is the power of 3 over 2, and you have to multiply by 2.285. Sorry, it's very annoying to use this kind of cursor. So if you want to calculate this one, we can try it. So I'm also trying it now. 40 exponential 40 exponent 3 multiplied by 0.24. Okay, divided by 0.03 multiplied by 0.06 to the power of 3 over 2. Okay, now I have to multiply by 2.285. Let's talk about this one. So I obtained 49.8 around that. So 49.8. So I already converted to megapascal here, and the unit should be megapascal to square root of M. So that will be the K1. So you have to fulfill everything because VP is already has been solved here. K1 also here, no worries, because the delta elastic here, nothing else here. So the formula is K1 square. So you know that it should be 49.8. The unit, if you quite confused, just write down the unit first, meter, and bear in mind should be to the power of 2. Okay, so to the power of 2 divided by 2 times sigma y. In our case here, where's it? So 800. I maintain, because this is megapascal, I maintain as the megapascal here. MPa. So this is how to solve it. MPa, and then you multiply by the E also maintain as the in a megapascal. The unit is gigapascal, so we convert into 210. Then we convert into megapascal. So 210 now mega 9, so it should be 1, 2, 3. So this is maintained as the mega pascal here. No worries, so it's quite clear here. Alright, so settle this one, settle this one to the power of 2, settle, and you have to multiply by 1 minus our Poisson ratio in the case is 0.3 now to the power of 2. So let's check what could be the possible answer for the delta elastic. So I know 49.8 to the power of 2, okay, divided by 2 times 800, and then I multiply by 210,000, okay, multiply by 1 minus 0.3 to the power of 2. I'm not sure, just check it. Okay, so this is my answer, 6.7 times 10 to the power of minus 6. Just check from the original script. Maybe I did it wrong. Oh, okay, it's cool. That's the same, 6.7 times 10 to the power of minus 6. So it's the same, 6.7 times 10 to the power of minus 6. Bear in mind, I already convert the unit in millimeter here. Alright, and same goes to the delta plastic. So sorry because I'm using the cursor, is quite slow. So this one is RP. The formula is RP. So RP we know is 0.4. Okay, and then W in the case we convert to because since that we're talking about, we just want to maintain it in a millimeter, so just straight away using the millimeter here. It's up to you. You can convert to the meter first. Okay, minus A in our case is 27. W minus A, 27. VP is already given straight away. You don't need to manipulating your graph because this is quite lucky. Meter here. So sorry, in millimeter, no worries because everything is in unit of millimeter. Divided by, sorry, the line is can be rough like this, is 0.4, and then again just copy the same thing, 60 minus 27. Now you have to plus with the A. A means 27 here. Okay, so we want to compare to this one. 0.4, 60 minus 27. You see from here is 13.2. This is a 13.2, and you have to multiply by 0.8 millimeter. Okay, you will obtain 10.56. This is 10.56 divided by the rest, 0.460 is a 13.2. 13.2 plus 27, you will obtain 40.40, 40.2. Then from here, the answer should be 10.56 divided by 40.2. You will obtain 0.263. 0.263 mm. So again, you know that the plastics displacement dominates the overall plastic deformation here, whereby the elastic deformation is very small. It's almost can be neglected. Alright, so when you combine these two, you'll know that when you combine these two, you will obtain the delta critical as, we know it's 0.263 plus 6.7 exponential minus 6, you will obtain almost nothing change, 0.263, the same, more or less. So 0.263 mm. So this is how you deal with the any exercise related to the experimental work of the CTOD. But this is only for the SENB, valid for SENB. If we change the specimen into the compact tension, you have to change this K1 calculation and whatsoever whatnots here. Alright, so I really hope that you got something from here. So please let me know. We will discuss it when we have our physical or face-to-face meeting, inshallah, by next week. And then we will continue with the J integral. This is another approach in obtaining the plastic deformation as well using the J integral, inshallah. I think by that, so thank you very much. Assalamualaikum warahmatullahi wabarakatuh.